This video is going to be on rate of change. In previous courses, you focused on a very specific type of rate of change, which was the average rate of change, and that is the average rate of change between 2 points. So this is your original m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So this is taking the rate of change between 2 points, specifically your points being x sub 1, y sub 1, and x sub 2, y sub 2. Okay, so this was a secant line that was connecting these 2 points, and what you found was the slope of that secant line. Now that was the average rate of change, but now what we're going to also be discussing is the slope at a single point. So specifically, if you zoom into t sub 1, if we were to draw a tangent line at t sub 1, we are going to be talking about the slope of that tangent line, in this case the m. Now we're not able to find the exact value of this slope, but we can tell that it is one of 3 values. So at t sub 1, we can see that this has a positive slope, so we can say that the rate of change of f at t sub 1 is positive. And now if we do the same thing at t sub 2, we can see that if we were to draw a tangent line here, the slope of that tangent line would be 0 because that line is flat. And graphically, what a constant looks like is going to be a flat line. So if we were to have a slope of 0, that would be 0x plus some constant, all right? We'll say b, which means y is equal to b, and that b value would be whatever this y is, okay? So that means the slope is going to be 0. So the rate of change of f at t sub 2 is 0. And the last possibility is going to be what we see at t sub 3. Now, if we were to draw a tangent line at this point, the slope of that tangent line would be negative. So the rate of change of f at t sub 3 is negative. So when we are observing the slope of the tangent line at these points, that is known as the instantaneous rate of change. And this is the rate of change at a single point, as opposed to the average rate of change, which is 2 points. Okay, so just a quick note. In AP Pre-Calculus, we can find the rate of change at a given point. And I need to correct this statement. This should say we cannot find. So we cannot find the rate of change at a given point because that would require calculus. So in this course, we will only discuss whether it's positive, negative, or 0. Okay, and if you plan on taking calculus, we use the first derivative to find the slope at a point, or the slope of the tangent line at a single point. Okay, so moving on to example 10. Example 10 says the figure shows the graph of a function f in the xy plane with 3 labeled points. Order the rates of change of f at the 3 labeled points from least to greatest. So least in this course is going to be most negative. The greatest is going to be most positive. So sometimes people might think of least as closest to 0, but in the context of this course, it will mean most negative. Okay, so at A, if we draw a tangent line here, we can see that the slope of that tangent line is going to be positive. So therefore, the rate of change, ROC, at A is positive. If we do the same thing at B, we can see that the slope of this tangent line is going to be negative. So the rate of change at B is negative. And lastly, at C, this is at the local extrema. So that means the average rate of, I'm sorry, not the average rate of change, but I guess more specifically, the instantaneous rate of change at C is going to be 0. So if we think about this, it's greater than 0 for A, less than 0 for B, and then equal to 0 for C. So when we rank these, we have the negative, which is B, the 0, which is C, and then the positive, which is A. The next picture, the figure shows the graph of a function g in the xy plane with 4 labeled points. One of the following points at which is the rate of change g the least. So again, least is going to be most negative. So if we compare the tangent lines at these points, A is going to be positive, B is also positive, C is negative, and D is negative. Now it's not going to be A or B because we want the least, which is the most negative. But if we zoom into C and D, yes, C is negative, but D has a steeper negative slope. So if we were to find the values for these constants for the slope of these tangent lines, D would have a slope that is less than C. Therefore, the correct answer is D for this one. All right, so multiple choice. The figure shows the graph of the function y equals h of x of the following. On which interval is the average rate of change of h the greatest? So 2 important words. We have average, which means we'll be using 2 points. We're going to be taking the average rate of change. And then we have the greatest, which is the most positive. So we can use our secant lines here in order to compare the slopes of these secant lines. So if we go from 2 to 3, we have 2 here and then 3 here. The average rate of change between these 2 points is going to be the slope of that secant line, and that's m is equal to 0. The next interval is from 3 to 5. So if we go from 3 to positive 5, if I draw a secant line between these points, the slope is going to be less than 0. So it's going to be negative. So right now, the most positive is going to be A. So I'm going to go ahead and X out D. I'm sorry, not D, B. If we look at C, we have 5 to 7. So from 5 to 7, let's connect that secant line. That is going to be m is greater than 0. And I messed up my notation for B. That should be m is less than 0. And then m is greater than 0 for the third one. So now the possible candidate is going to be C because the slope of the secant line for C is greater than 0, but for A it's equal to 0. Now D, we're going to go from 7 to 8. It's not looking promising because the slope of the secant line is going to be negative. Therefore, the only positive or the only secant line with a positive slope is going to be C. 13, the graph of the function f equals y of x is in the xy plane and always has a negative rate of change. All right, so negative rate of change, it could mean a few things. It could be linear, it could be concavity, negative rate of change. It doesn't specify that it's a continuous function, so it could be a plot, but still has a negative rate of change. And then which of the following definitions for the variable x and y would best model the function? Okay, so let's go ahead and take a look. So x is the age in years of a young child. Y is the height in inches of the young child. Okay, so we know that when children grow, they grow pretty quickly. Like they grow a little bit, and then they grow quickly, and then the growth tends to slow down. Okay, actually it should look like this. You grow a little bit, you grow quickly, and then you grow slower. Okay, so this is typically how people grow though, in this fashion. Okay, our function is decreasing, so a is not decreasing, therefore it's not a. Part B, x is the total number of points scored in a basketball game. Y is the time remaining. So this is interesting because we usually have time on the horizontal axis, but this scenario is suggesting that we have points on the horizontal axis and then time in the vertical axis. So as you go through a basketball game, the time is going down, and usually you want more points. So time is maximized at the beginning, and then it continues to decrease as the points increase, okay? If we were to switch these, time was here and points was here, then it would look something like this. The time would be increasing and the points would be increasing. Time is not increasing, I'm sorry. Oh no, time is increasing. Nope, time's going down. So this would be, that's why we can't do it like this, because in this scenario, the time is increasing when it needs to be decreasing. So that's why we're using this setup. Okay, that makes sense. Okay, so we can't do it this way. All right, so we'll come back to B. Part C, or choice C, says the time in seconds since a ball was thrown straight up in the air and the height in feet. You know this from Algebra 2. This is projectile motion. That is not strictly decreasing, so it can't be C. And then part D is the radius in meters of a circle. Y equals the area in square inches of the circle. So this is going to be increasing. This would actually be an exponential. As the radius grows, the area is growing more and more as we go through that, okay? So this is not decreasing. Therefore, the answer is B. All right, number 14 and 15 will require calculators. Now, this is a non-calculator unit. This is just to get into utilizing the technology and recognizing the graphs visually, okay? So I'm going to use a TI-84 for this. The ads are probably going to pop up. Yep. Okay, let me get rid of them, or try to. Okay, I thought I had this set up, but this always happens. I have to zoom out, delete everything, and then let's try to zoom back in. Okay, so it worked. Nice. Okay, so number 14 says the function k is defined by k of x, 3.16 plus 4.2x minus 0.85x squared for negative 10 to 10. Which of the following statements about k is correct? Okay, so let's go ahead and type this in. So 3.16 plus 3.16 plus 4.2x minus 0.85x squared. Now, usually I would say go hit zoom 0, but the vertex of this is within the window from negative 10 to 10. Okay, now from here, if I look at the first example, it says k has a positive rate of change over the interval from negative 10 to 8.348. First, you should be like, okay, where did they get that value? Well, we need the vertex in order to see where the function is changing, where the rate of change is changing, okay? So on this side, or the left side of the vertex, the slope is positive. The rate of change is positive. On the left side, the slope is negative. Rate of change is negative, so I need this coordinate point. So second trace, it's a maximum, hit number 4. I set my left bound on the left side of the vertex, and then I set my right bound on the right side of the vertex. And then I don't want to guess, so I hit enter again. Therefore, the coordinate here is 2.470, comma 8.348. Now the y value is, we don't need it, but just write the coordinate point if you want. What's really important is the 2.470. So part A is not going to be correct, okay, as it has a y value instead of an x value. K is positive. K has a positive rate of change, which means it's increasing over the interval from negative 0.663 to 5.605. I don't even know where they got those numbers, but they are not correct. K has a negative rate of change over the interval from negative 10 to 2.470. The interval is correct, but it has a positive rate of change. Okay, so that means the answer is D. K has a negative rate of change over the interval from 2.470 to 10, which is correct. That's the left side of the graph. Number 15, the table gives the life expectancy of U.S. females born in a given year over successive 50-year intervals. Over which of the following intervals is the average rate of change in life expectancy the greatest? So we're looking for the most positive. So this is going to require some calculations. So if I go back to my home, so second quit or second mode, part A says from 1800 to 1850. So this is a classic average rate of change problem. That should be the word that jumps out to you. So if I think average rate of change, I think y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Now the difference between all of the years is going to be 50. So the denominator should be 50 for all of these. If I look at part A, it says 1850 to 1800. 1850, it was 46.1. And then in 1800, it was 41.24. Divide that by 50. So 46.1, okay, 0.1 minus 41.24, and then divide by 50, I get 0.0972. If I do the same thing for part B, at 1900, the life expectancy was 53.63 minus the life expectancy in 1850, which is 46.1, and then divide that by 50, so we get 0.1506. Same thing for part C, 1900 to 1950, so we have 70.65 minus 53.63 divided by 50, and we get 0.3403. And if we look at 1950 to 2000s, in 2000, the life expectancy was 81.83. In 1950, it was 70.65. And then divide that by 50, we get 0.2236. So for this one, the correct answer is going to be C. So that's interesting. So from 1900 to 1950, the life expectancy of U.S. females born in a given year was higher than what it was in 1950 to 2000. So that, obviously this is just multiple choice, but this data is from real data. Okay, so most of the data that we use with our application problems come from real data, real research. So it begs the question, what happened from 1950 to 2000 where the life expectancy was less? So that might be something you learn in your history class, or it's something that you can look up on your own. All right, I hope this helps. The next video will be quite analytical, so we'll get into that tomorrow or whenever you watch the video. Hope this helps.